Hello! In this video, I'd like to talk about the computational complexity of some of the problems that students encounter in Calc 2 and Calc 3. And I first got really excited about looking into the computational complexity of things in calculus classes by thinking about the problem of switching bounds of integration. It feels like there's something related to Karnaugh maps, which are related to Boolean logic. It feels like there might be some sort of NP-complete problem hidden somewhere in there. And then there's also the relationship to implicit functions, right? If you have some sort of equation that defines a function, can we write it as a function of the other variables? Can we write one variable as a function of the other variables? And can we change up which variables we're writing as functions of which other variables? And those sorts of questions. So it's actually kind of tricky. I wasn't able to find anything particularly exciting in terms of switching bounds of integration. Feel free to let me know if you know of any interesting results related to the computational complexity of switching bounds of integration. But the thing that got me really excited and led down this really long rabbit hole was the problem of symbolic integration. This is as opposed to numerical integration, where we're interested in the numerical result of a definite integral. Here, we're just interested in indefinite integration. Given a formula, we want to be able to find a formula for its antiderivative. And of course, we teach heuristics for this in Calc 2. But they're just heuristics, right? In Calc 1, we teach an algorithm for differentiation. Students know exactly how long it's going to take, exactly what they're going to have to do, exactly what formulas they're going to have to take the derivatives of, and in what order, before they even start a differentiation problem. But that's in Calc 1. In Calc 2, we teach students a few tricks, and then you have to be really clever, and there are some problems where you have to be really clever, and there are some problems, there are some problems where you can't solve them at all. We know, for instance, that the formula e to the negative x squared, even though it's integrable in the sense that there is some function which is its integral, there is no nice formula for that integral, and we've proven that. And we call, so we give this function a name, we call it the error function, and so now it has a formula, but that's kind of cheating, right? We might be interested in saying, okay, is there an antiderivative for this just using pieces that we already know? And in some sense, this problem feels brute forceful, right? Our first intuition is we can kind of list out all of the possible formulas, and we can check their derivatives to see if they agree with the thing that we're trying to find its antiderivative. The thing that we're trying to find the antiderivative of, I'm going to call that the problem, even though the problem is to find its antiderivative. I'm going to call that formula also the problem. So, you list out all possible formulas. This is an infinite list, countably infinite list. You can do this in some sort of algorithmic way, and you just check one by one. You take the derivative of the thing in the list and check it against the problem, and if it agrees, then we found the antiderivative, and if not, we keep going down the list. And as long as you don't mind not halting in the case of, for instance, trying to find the antiderivative of e to the minus x squared, then this is a good way of doing it. I actually just want to quickly mention how computer algebra systems deal with computer algebra systems. Well, some of them are proprietary and we don't actually know how they work, but computer algebra systems use a whole bunch of different strategies in order to do symbolic integration. And one of the big ones is actually using something that's called holonomic functions. So a function is holonomic if it is the solution to some sort of differential equation where it's a polynomial times the ith derivative of the function plus some other polynomial times the jth derivative of the function, plus some polynomial times the kth derivative of the function, and so on and so forth. If some sort of combination like that is equal to 0 when we add it all up. And we can represent functions in terms of that list of polynomials and a little bit of extra data to tell us what solution we're looking at. This is a holonomic representation of the function. And the very nice thing about these representations, so first of all, they're closed under addition and multiplication. They're not closed under division, which is a little bit... they contain all of the algebraic functions, that is, any function whose graph is given by a polynomial relationship in x and y. A lot of implicitly defined functions showing up again. Sine of x, cosine of x, e to the x, natural log are examples of holonomic functions. Tangent is not. And then this also includes some kind of gross functions, the error function, the hypergeometric function, the Bessel functions, and the Airy functions. And you know, if the answer to a problem, to an integration problem, involves hypergeometric functions, I'm not going to be particularly satisfied unless you can say, oh no, I guarantee that there's no nicer way of writing this, that this is the nicest way of writing it. But if there's some sort of hypergeometric something that actually simplifies down, I don't want to hear about that. I want the simplified form. And the very nice thing is that this set of functions is algorithmically closed under integration. It's super easy, given a holonomic representation of a function, to find a holonomic representation of its integral. And so the issue here is just converting back and forth between the holonomic representation and is something a little bit friendlier. And in fact, this is implemented for Maple. This is implemented for all sorts of computer algebra systems. And it's also related to, there's a similar technique that's used to solve finite sums, and you can read about that in A equals B. Let's formalize the problem. I'm going to say that a formula is elementary if it's composed of addition, subtraction, multiplication, division, constants, and x, exponentials and logarithms, radicals, and trig functions. So this is an elementary function, and the question is, given an elementary formula, is there, and if so, can we find the elementary antiderivative? And of course, the answer is, well, I mean, our approach of writing down a list of candidates, actually, there's something there. Right? We can, for instance, define the complexity of a formula to be the number of symbols required to write the formula down. Any notion of complexity is fine as long as there's only finitely many members of each complexity class, and there's countably many complexity classes. And it turns out that if this is the case, then there's some sort of function that says, well, actually, we don't have to search infinitely long, right? There's some sort of n where if a formula has complexity, there's some sort of function f of n such that if a formula has complexity n, then we only have to check the formulas up to complexity f of n in order to find the antiderivative. If it exists, and if it doesn't exist, if we get to that end and we didn't find the antiderivative, then we know that the antiderivative doesn't exist. We know it's something like e to the minus x squared. So this is a fact, and this is well, it's kind of trivially true. So all you have to do, well, because there are only finitely many formulas of complexity n, we simply take the one that has an elementary antiderivative of the largest complexity, and that tells us how far we have to search. So this is, I mean, this is kind of silly, right? Because we want to know how far we have to search, and in order to find out how far we have to search, we actually have to solve all instances of the problem of complexity n. No, this is, I mean, this is kind of like a cheap math cheat at the problem. But, our intuition is that, well, actually, if we're taking an antiderivative, the complexity shouldn't be that much larger. I mean, we know some instances where the complexity increases, and it can increase quite a lot when we're taking antiderivatives. But intuitively, it can't increase too much, can it? So we're really interested in this question. What sort of function is this f of n, right? How much bigger can a symbolic antiderivative be? Can we put some sort of bounds on how far we have to search in order to find these antiderivatives? If f of n is some nice, reasonable function, then this is actually a really practical way of implementing this on a computer, right? You can actually list out all of the formulas of a particular complexity and then just check all of them. But it could be the case that f of n is some horrible function, but computable, in which case, well, it's not really practical from like a practical computing perspective, but at least it gives us an algorithm in the kind of mathematical sense of there being, this is a computable problem, but it's not practically computable. And of course, it could be the case that f of n is uncomputable, right? This seems a lot like some sort of busy beaver or halting problem sort of thing. It could be the case that f of n is uncomputable, in which case, well, we don't really know when to stop checking because we can't compute when to stop checking. And so it doesn't really help us in our search. We just have to keep on going forever. Well, actually, this function is really nice. Liouville proved that the possible antiderivatives for an elementary function are of this particular form. It's a really nice form. And Risch actually reduced that down to a finite computable collection of potential antiderivative candidates. So given a particular problem, we can list out a finite, very computable. This is just, I'm not something that you'd want to do by hand, but certainly something that the computer doesn't mind doing. Finite, nice list of potential antiderivative candidates, and then we just check the derivatives of each of those candidates against the problem. And we see, are these the same? Are these the same? Are these the same? And so on and so forth. Eventually, we'll find, if there is an antiderivative, we'll find it because it has to be on the list if there is an antiderivative. And if none of the candidates on the list wind up having derivative the problem, then we know that the problem actually doesn't have an elementary antiderivative. So if it isn't on the list, then it doesn't exist. And so we say, well, there is no elementary antiderivative to this particular formula. And this is good enough to be partially implemented in Maxima, Axiom, Sage, Mathematica. There are actually computer algebra systems out there that use this in part. They don't use it fully. Wikipedia claims that the Risch algorithm is in fact fully implemented in places, but I've seen other sources that suggest that it really isn't fully implemented anywhere. But it's good enough that you can run it on your computer. You can run the Risch algorithm on your computer. It's not the only algorithm that computers use to do symbolic antidifferentiation. There's a lot of easier heuristics that you want to try to apply first. Look up a list of common antiderivatives, try some really simple U substitutions or integration by partses. There's various things that you want to try first before you try the Risch algorithm, because it takes a little bit of time. But it is something that you can practically implement on your computer. So it turns out, after all of this, after the Risch algorithm, and we have what we thought was an algorithm, and it works. The Risch algorithm does in fact work. It gives you a list of potential candidates, and if none of the members of the list are the antiderivative, then there is no elementary antiderivative, and we can construct this list computably. After all of that, it turns out that symbolic integration of elementary functions is undecidable. What went wrong? How, like, I thought we had an algorithm. Um, uh, where does this go wrong? Well, it turns out that this actually goes wrong at the very last step. Um, it turns out that determining equivalence of elementary functions is undecidable. Remember, we have this list of potential candidates, and we're taking their derivatives, and of course we can take their derivatives, that's fine, but then we have to check the derivative with the problem formula. And we have to check to see if those two are equivalent. Now, of course, they might actually just be the same formula with all the same characters in the same places and the same tree structure. But it turns out that actually checking in kind of a more abstract case to see if these two formulas are the same turns out to be undecidable. And then using that, you can use some sort of integration argument to prove that actually if you had a decision procedure for symbolic integration of elementary functions, then you could actually, you would have an algorithm for determining equivalence of elementary functions. And so that proves that symbolic integration of elementary functions is undecidable, right? So this is Richardson's theorem. Uh, so actually everything's fine. The Risch algorithm works perfectly fine up until the last step where we're doing this equivalence checking. This equivalence checking actually winds up being undecidable. So let's get into some detail. A real formula is, so we're not talking about complex numbers, although there is some study of this involving complex, formulas that represent complex numbers. A real formula is said to be Richardson if it is composed of addition, subtraction, multiplication, rational constants, pi and x, and also contains the functions sine of x and absolute value of x. And you can compose these things however you want. So you could have, a sine inside of a sine or whatever. You just have, whatever formulas can be generated from these base components. And it turns out that checking equivalence of two Richardson formulas, or checking to see if a Richardson formula is equivalent to the zero formula, right? If this formula is identically zero, it turns out that that's undecidable, right? And because every Richardson formula is also elementary, this is kind of a sub-problem of determining equivalence of elementary formulas. But actually, it turns out that we're almost there. There's something called the Tarski-Seidenberg Theorem, which provides a whole bunch of stuff. It essentially provides an algorithm for solving pretty much any problem involving real functions. And it allows us to decide equivalence and zero checking and much, much more for real formulas involving addition, subtraction, multiplication, division, rational constants, and x, and also algebraic functions. So again, any of those functions that are implicitly defined so you have some sort of polynomial relationship in x and y, and that implicitly defines y as a function of x. So the only real difference between this set of formulas that we have here and the formulas here that were undecidable, right? Checking equivalence of these Richardson formulas is undecidable, whereas checking equivalence of these just purely algebraic formulas is decidable. And the only real difference is that over here we have sine of x, right? Absolute value of x is an algebraic function, so we have that in both cases. Over here, the real difference is that we have pi, and we also have sine of x. And what's going on here is actually the thing that goes wrong with these Richardson formulas is that because you can talk about sine, you can talk about the integers. Right, the integers are just values of x where sine of pi x is equal to 0. And so this allows you to talk about integers in ways that these formulas here, these algebraic formulas, can't. And that's the issue. it turns out that there's this real kind of counterintuitive fact when it comes to decidability, that when we're dealing with questions involving real numbers, things tend to be very decidable. And when we're dealing with questions involving integers, and again, the point was that sign allowed us to talk about integers. When we're dealing with problems involving integers, they wind up being undecidable. Kind of the big example being that arbitrary questions in first order logic about the integers are undecidable. That's Gödel's incompleteness theorem. And multivariable polynomial equations, we call them Diophantine equations when we're dealing with integers, are undecidable due to the negative result to Hilbert's 10th problem. And so if we're dealing with integers, these sorts of questions wind up being very undecidable. On the other hand, if we're dealing with reals, these sorts of questions wind up being very decidable. If we have an arbitrary question in first order logic involving just the real numbers, not the integers, we can decide it. That's the Tarski-Seidenberg theorem. And if we have a multivariable polynomial equation in the real numbers, we can determine if it has solutions or not. And that's kind of a sub-part of the Tarski-Seidenberg theorem. Of course, if you actually want, a concrete, what are the solutions? Well, okay, then you have to get into numerical analysis and things like that. But you can determine if a system of multivariable polynomial equations over the real numbers has a solution using Tarski-Seidenberg. So it's this really, and it's kind of contradictory, right? It's counterintuitive, the fact that when we add more stuff, things become more decidable. But that's just the way things are. Integers wind up being very undecidable. Real numbers wind up being very decidable. And of course, if you're interested in polynomial equations over the complex numbers, does this complex polynomial have a root? And then the answer is, yes, it does. The whole point of complex numbers was that our polynomials would have roots, and it's really easy. I mean, of course, there are some instances, constants that aren't zero, things like that. But for the most part, determining if a multivariable polynomial equation has solutions over the complex numbers, super easy. I also want to quickly mention equivalence checking in practice, right? So I said that this was undecidable, but if you're taking a math course or if you have taught a math course recently, you're probably familiar with online homework systems that require students to enter formulas. And you say, well, hold on, didn't you just say that it was undecidable to check to see whether one formula was equivalent to another formula? And surely what these homework systems must be doing is they take the formula that the student enters and check to see if it's equivalent to the answer that's in the database. Right, so there's equivalence checking that has to happen in order for this homework system to work properly. Well, it turns out that equivalence checking in practice with these sorts of applications winds up working by plugging in random points. And of course, we only know how the non-proprietary homework systems work. Proprietary homework systems, we have no idea how they work, but they probably use the same algorithm in order to check equivalence of students' answers. And it turns out that this is actually pretty good, right? You can plug in a bunch of random points, and if the two formulas agree everywhere, then we know that the two formulas are in fact algebraic. Well, they're probably algebraically equivalent. Maybe they're not, but probably. So for instance, Khan Academy's cast.js, it uses a number of techniques, but one of the techniques that it uses for equivalence checking is by plugging in random points. And what this means actually is that if you have two formulas that are almost equivalent to each other, here I have an instance of formulas that are almost equivalent to each other, but there's like an absolute value in there. it returns true non-deterministically because it's actually picking actually random points in order to determine equivalence. So that's a fun thing you can do, and you can play along with that at home. I'll link that below. Chimera uses something called mathexpressions.js, which uses the same technique, and WebWork also uses this technique of plugging in a bunch of random points. And this is kind of an interesting thing to think about, this question of how many points do we have to plug in, and how do we determine which points we should be plugging in, and what's the computational complexity of that. Those are fun questions to think about as well. Although, again, for practical purposes, the real key thing is that you don't want any false negatives, right? You don't want it to be the case that the student enters an answer that is correct and they're told that it's wrong because you tried to do some algebraic manipulation and you weren't able to get the student's answer to look like the answer in the database. Students are going to be a lot happier if you occasionally, very rarely, give them a false positive, right? Their answer is wrong, but you tell them that it's correct, and that's okay. Students aren't going to mind, and maybe won't even notice. Yeah, so it's a clever thing, right? If we were trying to do some sort of algorithmic, symbolic equivalence checking, then it would actually be, we would get a bunch of false negatives instead of false positives, and we don't want that for these online homework systems. So really quite clever. And one of the really cool things is that you can keep modifying these questions. You can modify questions about what sorts of formulas we're trying to take the antiderivatives of. For instance, you could say, oh, well, I'm just interested in polynomials. Well, there is an algorithm for taking the antiderivative of polynomials. That one's really straightforward. So you can change up, if we're doing integration, you can change up the sorts of formulas that we're working with. And there's all sorts of, you can add a new function, you can get rid of functions, you can restrict how we're allowed to compose functions together. There's lots of different ways of modifying that particular problem. You can also, when we're trying to check equivalence of formulas, right? So one of the things you can do is you could check if some sort of formula is ever equal to some other formula, right? The problem that we were interested in was, are these two formulas identically equal? That is, are they equal for all x? But you might want to check, oh, are they equal for some x or for almost every x? You could want to check, for instance, if one function is always larger than another function. Again, you could change up the set of generators for the functions. You can change up the number of variables. You can change the domain. Integers tend to be undecidable. Rationals tend to be, we don't actually know a lot of answers. As far as I'm aware, the negative result for Hilbert's 10th problem is still open in the case of rationals. For reals, things tend to be decidable, and for complex numbers, things tend to be really nice, actually, because, complex numbers, complex polynomials, it's really easy to find solutions to those. So by changing up the domain that we're considering, we can radically change the problem from completely undecidable to actually really nice. And so there's kind of this space that we're carving out. And from one end, we're saying, okay, like these things over here happen to be very decidable. And there's nice algorithms for them, and we keep carving away, like here's something else that we've proven is decidable, here's something else we've proven is decidable, and then on the other end of things, we prove that a bunch of things are undecidable. So we say, okay, this is undecidable, and this is undecidable, and this is undecidable, and of course there's some gap in the middle that we're working our way inwards towards, where we just currently don't know, and it's really kind of interesting to see how small changes in the problem can move us around between these three regions, where things are known to be decidable, things are known to be undecidable, and then of course this gap in the middle where we don't really know what to expect yet. So it's fun changing up these problems and seeing, although there really isn't too much research into this. There isn't a lot of we don't have as much information as you might want in terms of there's a lot of unknown gap that probably could be resolved if a lot more mathematicians worked on it. So I encourage you to work on this, because this is fun stuff, right? It's basic mathematics, but we're doing some really high level reasoning about it. So I thought this was quite fun. Hopefully you found it fun as well. And if you have any results that you know about that I haven't mentioned in this talk, please let me know. And if you discover any results that I haven't mentioned in this talk, please let me know, because these are fun problems.